Okay, now let's look at another very important basic concept in forecasting. So you see I have now done the logarithm of the air passenger series, which changes it a bit. And now what the lower plot shows us, this is called a lag plot, so it's a bit difficult to read, but we have here x at time t, and we plot that against x at time t minus 1. So basically we always plot one value and the value before that. And now we see that there's actually this quite nice linear relationship between those. And that's obviously something we could use for forecasting, right? So we could say, well, if we have x at time t minus 1, so if we know there's a relationship with the next value, we can use that for forecasting. Very similarly, x at time t and x at time t minus 12, right? I mean, I said before that this series is a monthly series and it has this yearly seasonality. So this, what you see here, this shape here, that's always kind of 12 months. So again, here we see kind of this linear relationship between the two that could be used for forecasting. And yeah, so with that we can calculate the autocorrelation, right? So autocorrelation is just the correlation between lags. For example, as we've seen, between t and t minus 1 or t and t minus 12. Correlation measures the extent of a linear relationship. And it's usually calculated between xt and all lags up to some maximum number of lags. And then it's put into a plot. And the trend is then usually visible in these plots as large autocorrelation in the first lags that slowly decreases, and seasonality is large autocorrelation in seasonal lags, right? And if a series has both trend and seasonality, it's just a combination of these two. To give you an example, that's how it works. So basically here is 0, and this is somewhat close to 1. And now every bar, so the first bar is our lag 1, the second bar is our lag 2, lag 3, and so on. And as I said, this series has a trend, so you see it's kind of slowly decreasing the autocorrelation, and then here around lag 12, you see it's kind of going up again. Okay, that's the autocorrelation. And now you have something else that is called partial autocorrelation, which is what is shown here in this second plot, where the idea is, for example, for lag 2, sure, lag 2 has a lot of correlation with lag 0, with the current value, but that's only because there's a lot of correlation in lag 1, right? So because if lag 1 has a lot of correlation, that means there's a lot of correlation between the current value and the one before, and there's a lot of correlation between the value one before and the one before that. So it kind of translates like this. So the partial autocorrelation, what that does is that it subtracts this correlation that is kind of already explained by earlier lags. So lag 1 is the same because there's nothing to subtract, right? So this first peak is the same. And now we see that the other lags, they are now very small. Only we have this kind of significant lag 13. And you know, well, the question is now, why is this lag 13? Shouldn't it be lag 12? That's an interesting question. It's a bit a technicality of how this partial ACF works. But yeah, the answer is basically if there's a lot of correlation in lag 1 and in lag 12, then that shows up in the partial autocorrelation lag plot as a lag 12 plus 1, which is 13. Okay, ACF and PACF for random walks. So again, here some random walk, and we see it has like lots and lots of correlation slowly going down in the ACF plot, and then in the PACF plot it has a lag 1 and nothing else, right? And so yeah, that's important to understand, that in a random walk, lag 1 tells you a lot because that's your naive forecast, that's where you are currently at. But then all the other lags, they don't tell you anything. Even though in the ACF plot it looks like there is, like, you know, all of this autocorrelation that we should somehow model. No, not how it works. Okay, so this brings us now, to like the linear models, right? I mean, I've said it, like if we have a lot of correlation in lag 1 and lag 12, then why don't we build a linear model with lag 1 and lag 12 to forecast the next value? And that's exactly what an AR model does. So ARMA, that stands for autoregressive moving average. So it has both an AR part and an MA part. Okay. This is the AR part, where you see this is just the linear model of the lags, right? Like to predict xt plus 1, we build a linear model from xt back to xt minus p plus 1, you know, just the amount of lags we want to use. And now we have these coefficients in the linear model. Okay, and now the MA part, the moving average, that is also a linear model, but now in the errors, right? So the error at time t, the error at time t minus q. So the ARMA model is linear in both the lags and the errors. However, if you ever try to implement an ARMA model from scratch, you will find out that when fitting this model, where do the errors come from, right? I mean, the lags, that's obvious. That's just our time series. But these errors, you are kind of generating them while fitting. So in the end, you actually need to estimate some initial conditions and then step through the whole series to fit an ARMA model. That's in ETS the same. You also need to estimate initial conditions and then step through the whole series. There is no closed form solution, so it actually needs a nonlinear fitting procedure. By default in R, that's BFGS fitting. And that can actually be quite slow in long time series. So if you have like a time series with 1 million data points and you fit an ARMA model on that, it can be really slow. And yeah, and it's the fitting is non-linear. So if people tell me, well, ARMA, that's linear, well, that's a very relative statement. Okay, so there is this result, a very important result in the literature, that any stationary AR1 model has an equivalent MA infinity model, and any invertible MA1 model has an equivalent AR infinity model. And what that means for us is we can approximate the MA part of the ARMA with a higher order AR part, right? And it turns out that in practice, this higher order is often not very high to get good results. I mean, in econometrics, 5 is often already seen as a high order of an AR model. It's much more common to use AR2, AR3, and then you use an AR5, and they would be like, oh, that's a quite high order. So I see ARMA more as some sort of reparametrization to get fewer parameters and a smaller input window. But it's at the cost of more complex model fitting. So if you have a very long time series, there's really no point in fitting ARMA. Just fit an AR model with a very large input window. It will fit so much faster and it will give you very similar results. And if your series is super long, there's no problem in using a long input window, and which means many lags, right? So I have been using models. I have been training models on daily time series where you want to capture the yearly seasonality, and you just use an AR 400, for example. Okay, so the next thing are ARIMA models. So we now have this I, right? So we've seen what ARMA is, but now what is the ARIMA? The I stands for integrated. where the question is, do we want to model the values directly or the change to the last value? This addresses non-stationarity, and we'll get to what non-stationarity is in a later chapter in the machine learning chapter, but just, well, as a quick explanation now, stationarity basically means that the statistical properties of the series don't change over time, and then non-stationarity means they do change. So for example, a trend is a change in the mean, seasonality is also a periodical change in the mean, so trend, seasonalities, that would be non-stationarities. And you can see this as a pre-processing step, right? So you do the differencing of the series before we then do the ARIMA. And the advantage of doing that is hopefully it will make the series stationary. I mean, it not always does that, but often it does. And the disadvantage is we lose some information about the scale in the pre-processing. Yeah, so, and differencing to make series stationary, that's something that is very, very common in economics. And I think that's because the series there often have this kind of random walk type behavior, and there obviously differencing does make them stationary. So here we see, yeah, top panel is a random walk series, and now we do the differencing, and now we get just the innovations, which in the way we simulated this data, the innovations are just independent, identically distributed. Random numbers. Okay, and now if we look at the ACF and the PACF of this differenced version of the random walk, we see that there is just nothing in there, no correlation on any significant level. So nothing we could use to really forecast this series based on past values. Good, so now let's run this differencing on our air passenger series, and we see it did a good job of getting rid of the trend. However, the variance is still growing, right? So basically you see kind of like this. So the variance here at the end of the series, it's a lot higher than the variance kind of at the beginning of the series, right? So here, a lot more than here. So what could we do about that? Well, one thing that people would usually do is a logarithm.